Okay, so we're going to be doing problems that have to deal with the Hasselbach equation because usually there are other ways to solve these buffer and titration problems. However, the Hasselbach equation is probably the easiest way to do them. And there are some problems where you really need the Hasselbach equation to know some things like, say, the ratio between these two or what the pK of A given only this information. Well, you can figure out what the pK of A is. P of H, you have the concentration of H, and then you have the concentration of these two, and then you could just plug them all in and solve for pKa. Remember, there's some other twists thrown in there too when you do that, but this is probably, you don't have to worry about very much if you use this equation. You need to know how and when and why this equation is, or it came out to be. Anyway, let's do an example using this equation. So a sample of D.71 times 10 to the negative 3 moles of an acid is dissolved in 25 milliliters and titrated with this molarity of sodium hydroxide. After this much of the base are added, pH was found to be 4.76. So what is K of A for the unknown acid? So we need to know what K of A is. So we can use this equation to figure that out, can't we? So P of H, we have, and this is like my 4th attempt at this video because computer hates me. So 4.76, that's a 4, not a 9, or, yeah, my handwriting is bad. We need to solve for what pK is, but how do we solve pK of A using pK of A? Right, pK of A, and this is true for any p of something, is equal to the negative log of K of A. So that means that we could just say that K of A, if we divide both sides by -1 and then raise both of them to the 10 to that power, equals 10 to the negative pKa power. I don't know if you can see that, but it's pKa. I'll do it in a different color so you can see it, but pKa. Yeah. Alright, so we have that established. So, now we have the concentrations of these two to worry about. So how do we do that? Well, we have a base being titrated with acid. And if you remember from titrations from before, an acid plus a base makes that acid's conjugate base plus water from all the titration problems we've been doing. From the handwritten notes or whatever videos or whatever you've been doing. So, we also know that the limiting reagent gives us the number of moles for the conjugate base or acid or whatever it is. So the conjugate something. So we just figure out the number of moles for NaOH, and that gives us the number of moles of the base that was involved. So 0.0901 times 0.0149, remember you need to do it in volume, 1.34 times 10 to the negative 3 moles. Now also, and this is just basic stoichiometry in case you didn't know. Now also we need to figure out what the molarity of the conjugate base is. Otherwise we can't use this equation. So how do we do that? We'll take the number of moles and divide it by the total volume. Why not just this volume or this volume? Well, because they've already added together and they've already reacted, and this is how much we got. So total volume, in case you didn't know, is 39.39 milliliters, which is equal to 0.033. I keep on making that mistake for some reason. Liters. So 0.0399 liters. And that gives us, if we did it right, wrong button, divided by 0.0399. It gives us 0.0336. 0.0336 m, and that is for the base. Okay, so we have the concentration of the base. Now we need to figure out what the concentration of the acid is to plug that in there. Well, how do we do that? We know the total volume is 0.0399 because that's what we discussed here. Now to figure out the concentration, we need to know the number of moles. Well, we have the number of moles here, right? So can we just do that? No, we can't. That's right. Because the reaction took place, so this changed actually. how much did it change? Well, if you remember stoichiometry, which is one of the basic forms of, well, it was one of the basic things that you need to know in chemistry, 0.0901 times 0.0149. Okay, so this is the number of moles. This is the number of moles of the base, right? So, and that's being reacted with the acid. Well, can't we just subtract them? 0.0271 in positive number, because it's the same thing either way. But yeah, this is the concentration of the base. So not the base, the acid. 1.37 times 10 to the negative 3. And realize that this is an unknown acid. We don't know what the heck the acid is. And it doesn't really matter. We're just solving for the KFA. So we take that and divide it by the total volume, 399. That gives us 0.033. 0.0343 m, and this is for the acid. Now we can plug and chug to solve for this. So P of H equals pKa plus log of the base over acid. Trying my best here to write the best I can, but making no promises. Oh, okay. So we know the pH is 4.76, right? It's 4.76. That is equal to the pKa. Now, what is the log of this business right here? Too dark. I'll just do that. What is the log of that business there? Well, I'm just going to use approximations here, because I'm about to retype all that. 443. Or no, not 443. 343. Remember, it's the concentration of the base, which is 0.0336, divided by the concentration of the acid. And that gives us this ratio between them. Now we need to do log of that, though. So where's the log of that? Right here. So this is what that value is. So negative 0.009. And then if we solve for pKa, we can go ahead and say that pKa, this is about 0.01, so plus 0.01. That is about equal to, and I'm just using a random color, I don't know where, 4.77. Well, so we found pKa. How do we find kVa? Using that equation right there that we already solved for. So, and I'm using yellow now, kVa is equal to 10 raised to the negative 4.77 power, which is equal to, and if you get out a calculator, it would be 10, and I'm approximating here again. Oh shoot, forgot the minus sign. Yeah, if that happens, you know, whoa, that's not right. 1.7. If you didn't catch the end of it, sorry. Times 10 to the negative fifth, and that's K of A. So we found the answer. Had we been more exact, the more exact answer would have been 1.71. So we know we were pretty darn close. I mean, we got 1.6985, for goodness sake. We were pretty darn close to this. And they both rounded this anyway, so we can go ahead and use this for overall. Alright? So that's one form of question you would see, and for other forms, you'll just have to watch the next video.